Hi, this is Mrs. Dorman. We're going to talk about sampling distributions of proportions. So what's the shape, center, and spread of a sampling distribution of a proportion, and also just what is a sampling distribution of a proportion? So if we take a sample from a population and had a sample proportion and we started graphing all of those, if we could just take many, many samples over and over again, in fact, if we could take every single possible sample from the population, we would get the sampling distribution if we graphed all of those. Just some notation at the beginning that P represents the population proportion. When we take a sample and get a sample proportion, the symbol we use for that is P hat. So that means the sample proportion. So if we took many, many samples, in fact, if we took all possible samples of size n, and by the way, they need to be random samples, simple random samples, so SRSs of size n. So if we took all possible samples of size n and started graphing them, all of those p hats, all of our sample proportions, we would get the sampling distribution. And the shape of that sampling distribution would be approximately normal if there's a condition that's true that's called the large counts condition. So for shape, it's approximately normal if the large counts condition is met, and that is if n times p and n times 1 minus p are at least 10. That's called the large counts condition. So n sample size times p, the population proportion, needs to be at least 10, and then n, the sample size, times 1 minus the population proportion is at least 10. So there's this relationship between the sample size needs to be a certain size or big enough times the product of the population proportion. The product of those together needs to be at least 10 in order for the shape to be approximately normal. Otherwise, the shape of our sampling distribution could be skewed. The center is the mean. We're going to use mean for center. So if we had our sampling distribution and found the mean of all of these p hats, they should be all centered around p, the true proportion. So the symbol that we use for that is mu, because that means mean, sub p hat. So that means the mean of the sampling distribution of proportions. That's just p. And then the shape, or sorry, we already did the shape, the spread is how spread out all of our p hats are, and that's the standard deviation sub p hat, sigma sub p hat. It means the standard deviation of all of the p hats, standard deviation of the sampling distribution of proportions. There's a formula for it. The square root of p times 1 minus p over n. And there's also a condition in order to use this formula for the standard deviation of the p hats, and that's called the 10% condition. And the 10% condition is that the sample size n needs to be no more than 10%, so I'll use 1/10 of the population proportion. I'm using big N for the population proportion. So this is called the 10% condition, and this is also if we're sampling without replacement. Which is typically how we are sampling if we're sampling people, for example. We would be sampling from a total population of a group of people, and when we're taking our sample, we're not putting that person back in and possibly choosing them again. If we were, so maybe that happens if we are rolling dice or maybe we're flipping a coin, then we're not really sampling from like a larger population of dice. We're just kind of using the same die over and over again. Then we don't really need to check the 10% condition. Each die roll is just independent. You're just kind of using the die over again. But typically we're sampling from objects or people, and we do need to check the 10% condition. So we have three things going on for the description of the sampling distribution, and that is the shape and the center and the spread. So the shape is approximately normal. The center is mu sub p hat, and that's p. And then the spread is sigma sub p hat, and the formula for that is the square root of p times 1 minus p over n. And then there's three conditions that we're checking for. First, that it just needs to be a random sample, a simple random sample, an SRS. The large counts condition needs to be met, and the 10% condition needs to be met if we're in a situation where we are sampling without replacement. So let's try some examples. The superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend a four-year college or university. What is the probability that an SRS of size 125 will give a sample proportion of at most 75%? So the P, the true proportion for all middle school students, is 0.8. So I'm going to write that down first. Before we can figure out the probability that we take a sample of size 125, and actually I'll write that down too, our sample size N is 125. We want to find the probability that we take a sample and it is at most, or another way of saying that is no more than 75%. Before we can do that, we need to figure out the shape, center, and spread of the sampling distribution, and also check that the conditions are met. So let's start with the shape. And is it approximately normal? So in order to check for that, we need to check the large counts condition, and that's that N times P is at least 10. So N is 125. I'm just going to go ahead and start plugging in numbers. P is 0.8. Is that at least 10? 125 times 0.8 is 100. So yes, that's at least 10. Just going to put a little check mark. And then N times 1 minus P also needs to be at least 10. 125 times 1 minus 0.8, which is 25. Yes, that's at least 10. So the large counts condition was met, and yes, our sampling distribution is approximately normal. So I'll just get rid of that question mark. What's the shape of the sampling distribution? And actually I'm going to go ahead and start drawing a normal curve because we're saying that the shape is approximately normal. So what's the center of the sampling distribution? The symbol for that is mu sub p hat. That means the mean of the sampling distribution of proportions. That's just p, 0.8. And then the spread of the sampling distribution is the standard deviation, sigma sub p hat, the standard deviation of sampling distribution of proportions. The formula is the square root of p times 1 minus p over n. So square root of 0.8 times 1 minus 0.8 over 125. And that is 0.036 about. And in order to use that formula, we actually want to check the 10% condition. Is the 10% condition met? Well, we need to know if the sample size is no more than 10% of the whole population. The sample size is 125, but it doesn't tell us what the whole population is, but we can kind of make some assumptions as long as they're reasonable. So the population is all middle school students in the whole district. In order for the sample size to be no more than 10% of that population, the population needs to be at least 1,250, 10 times as much as 125. And I'm going to say yes, we can assume that all middle school students in the district is at least 1,250. So we can just write that in words. We can just say that we can assume that there are at least 1,250 middle school students in the whole district. Okay, so now I'm going to start doing the calculations for probability. So we want to know the sample proportion is at most 75%. So I'm going to mark 75%, 0.75, and at most means, another way to say at most is no more than, or the maximum it could be is 0.75. So we're looking for this area, this tail area. First we need to find the z-score for 0.75. And in general, the formula for a z-score is the value minus the mean. You figure out how far away the value is that you're looking for is from the mean, divided by the standard deviation, which was 0.036. That is about negative 1.39. So 75%, if we were going to interpret that, 75% is 1.39 standard deviations below the mean, but we really want the probability that we get 0.75 or lower. So we can either take our z-score and look up that value in the normal distribution table, or on the calculator, we look for normal CDF. And then the lower bound would just be some low number. We usually put maybe like negative 1,000. And then the upper bound would be our z-score, negative 1.39. And we get about 0.082. So there's about an 8.2% chance that we get a sample proportion of at most 75%. All right, we're going to try one more example. Power companies severely trim trees growing near their lines to avoid power failures due to falling limbs in storms. Applying a chemical to slow the growth of the trees is cheaper than trimming, but the chemical kills some of the trees. Suppose that one such chemical would kill 20% of sycamore trees. The power company tests the chemical on 250 sycamores. Consider these an SRS from the population of all sycamore trees. What's the probability that at least 24% of the trees in the sample are killed? All right, so just like the last problem, we want to figure out the shape, center, and spread and see if the conditions are met. And then we can figure out this probability part using a z-score and normal distributions. So let's start with the shape and center and spread. In order to figure out if the shape is approximately normal, we want to test the large counts condition. And that's that n times p is at least 10, and n times 1 minus p is at least 10. The sample size was 250. And p, the true proportion, the population proportion, is 20%, so 0.2. That's 50, which is at least 10, and then n times 1 minus p would be 250 times 1 minus 0.2, which is 200, and that's also at least 10, so our shape is approximately normal. Again, this condition is called the large counts condition. How about the center? The mean of the sampling distribution of proportions is p, the population proportion, 0.2. And the standard deviation of the sampling distribution of proportions, if the 10% condition is met, which I'll check in just a second, is the square root of p times 1 minus p over n. So square root of p was 0.2 times 1 minus 0.2 over n was 250. Okay, so was the 10% condition met? That would mean that the sample size is no more than 10% of the whole population. The sample size was 250. Can we assume, it's not telling us the whole population of sycamore trees near the power lines, In order for 250 to be no more than 10% of the population would need to be at least 2,500. And again, I'm just going to say yes, we can assume that the whole population of sycamore trees that this company deals with, or that grows near the power lines, is at least 2,500. It's okay to just make like a reasonable assumption. So again, I would just say yes, the 10% condition is met. We can assume that there are at least 2,500 sycamore trees in the population. Okay, so now we can do our calculations. We have a normal distribution. The mean is 0.2. And we're trying to figure out the probability that at least 24% of the trees in the sample are killed. So I'm going to mark 0.24. At least means that number or greater. So we want this tail up here. We need a z-score. We take the value minus the mean divided by the standard deviation, which we already calculated was 0.025. And for that we get 1.6. We can either go to the table and look up 1.6 for the z-score and see what area we get. If we do that, we're going to get this area here, and then we would want to do 1 minus that proportion to get our final answer. We can also go to the calculator and go to normal CDF. I'm kind of running out of room, so I'll just write it up here. We would use 1.6 as the lower bound because we want everything above that, or at 1.6 or more. So 1.6 our z-score for the lower bound, and then just like a big number for the upper bound. And when we do that, we get 0.055 about. So about 5.5%. Again, the question was, what's the probability at least 24% of the trees in the sample are killed? It would be about 5.5%. Again, if you use the table, you're going to get the proportion that's less than 24%, less than the 0.24, and then you would just subtract that from 1 to get our final answer here, because we want this upper tail shaded area.